In this video, we're continuing our discussion of ordinary differential equations. We're still discussing solution methods for initial value problems. And in particular, we're going to introduce multi-step methods. So the Runge-Kutta formulas that we introduced in the previous videos obtained higher accuracy through the use of several function evaluations. However, higher order accuracy can also be achieved by using data from prior to the time step ti. So if the solution and or the function at ti minus 1 or ti minus 2 are also used, then it helps us to achieve higher order accuracy. And this is the idea with multi-step methods. So this is another way of providing additional information about f. And the apparent price for higher order accuracy is the use of additional computer memory, which can be of concern for partial differential equations. It's important to note that multi-step methods are not self-starting, so usually another method such as explicit Euler is used to start the calculations for the first or first few time steps. So a classic multi-step method is called the leapfrog method, and it is defined as shown here. So x at I plus 1 is equal to x at I minus 1 plus 2h f at xi ti. And for a single time step, it is order h cubed. So the method is second order accurate globally. So given an ODE, x prime is equal to f of x and t, the leapfrog method is derived by applying the second order central difference formula for x prime. So as I said, the leapfrog method is a second order method globally. So starting with an initial condition x0, a self-starting method like the Euler method is used to obtain x1, and then leapfrog is used for steps 2 and higher. Applying the leapfrog to the model equation, x prime equals lambda x leads to the difference equation shown here. So xn plus 1 minus xn minus 1 is equal to 2 lambda h xn. So we assume a solution of the form xn equals sigma to the power n x0, and we can substitute this into our difference equation, which leads to the expression here, sigma to the power n plus 1 minus sigma to the power n minus 1 is equal to 2h lambda sigma power n. And now we can divide by sigma to the power n minus 1, and we get sigma squared minus 2h lambda sigma minus 1 is equal to 0. And this quadratic equation can be solved to find the two roots, sigma 1 and 2, which is equal to lambda h plus or minus the square root of lambda squared h squared plus 1. So having more than one root, as we do here, is a key characteristic of multi-step methods. For comparison with the exponential solution of the model problem, we expand the roots and powers of lambda h. So let's look at the first root. Sigma 1 is equal to lambda h plus the square root of sigma squared h squared plus 1. This can be expanded as shown here, which is equal to 1 plus lambda h plus 1 half lambda squared h squared minus 1 over 8 lambda 4 h4, etc. The second root is lambda h minus the square root of lambda squared h squared plus 1, and it can be expanded as shown here. Now this first root shows that the method is second order accurate, as we match our exact solution up to the second term here, so the lambda squared h squared over 2. The second root is a spurious root and is often the source of numerical problems. So you can see that even as h goes to 0, the spurious root is not equal to 1. So we get, as h goes to 0, the spurious root starts with this minus 1 here. So for lambda real and negative, the spurious root has a magnitude greater than 1, which leads to instability. So we can see that here. So if lambda is real and negative, then this value is negative, and this value is, and then we're subtracting something that's bigger than 1, so we know that this is going to be a negative number with a magnitude bigger than 1. So this leads to instability. Now, since the difference equation that we had for xn is linear, its general solution can be written as a linear combination of its solutions. So xn is equal to c1 sigma 1 power n plus c2 sigma 2 power n. The solution is composed of contributions from both the physical and the spurious roots. The constants c1 and c2 are obtained from the starting conditions x0 and x1 by letting n equals 0 and n equals 1 in this equation, respectively. So if we let, with n equals 0, and we get this equation here, x0 is equal to c1 plus c2, n equals 1, we get c1 sigma 1 plus c2 sigma 2. And these can be solved to find these constants. So c1 is equal to x1 minus x0 sigma 2 over sigma 1 minus sigma 2, and c2 is equal to sigma 1 x0 minus x1 divided by sigma 1 minus sigma 2. So for the model problem, if we choose sigma 1, x1 is equal to sigma 1 x0, then the spurious root is completely suppressed. So that would make, if we had this would make this part 0, so then we would get c2 is equal to 0, which means that the spurious root would be suppressed. In general, we can expect the starting scheme to play a role in determining the level of contribution of the spurious root. It's important to note that even if the spurious root is suppressed initially, round-off errors can restart it again. So in the case of the leapfrog method, the spurious root leads to oscillations from one step to the next. So again, these are our roots, sigma 1 and sigma 2. We can see that the first root is unstable for lambda real and positive. So if lambda is real and positive, then this is some positive number, and this is a positive number bigger than 1. So we can see that the magnitude of sigma 1 is greater than 1 if the real part of sigma is greater than 0, is positive. So this means it is unstable. The second root, we already saw that it is unstable for lambda real and negative. So this means that only purely imaginary lambda h lead to stability. So let's look at the application of the leapfrog method to the case where we have this purely imaginary lambda. So lambda is equal to I omega. In this case, we get sigma 1 and 2 as shown here. So I omega h plus or minus the square root of 1 minus omega squared h squared. Now, if omega h is less than or equal to 1, then sigma 1 and 2, or the magnitude of sigma 1 and 2 are equal to 1. So this means there's no amplitude error. And this is the main reason for using the leapfrog method. If the magnitude of omega h is greater than 1, then the magnitude of sigma is, as shown here, which is greater than 1, and the method is unstable. So if this is bigger than 1, and this is bigger than 1, then that means this is going to be something positive, and so then we will end up getting something that is unstable. So the leapfrog has a very small stability region, which is only along the imaginary axis. So just between these limits of plus and minus 1, only on the imaginary axis. So it has a very tiny stability region, so it tends to not be very useful, but it can work for purely oscillatory solutions. The other multi-step method that we're going to consider is called Adams-Bashforth method, and it's a second order method. So let's consider the Taylor series expansion of xi plus 1, as shown here. Now we can substitute x prime I is equal to f of xi and ti. And for the second derivative, we can use the backward difference formula and substitute this in here. So f xi ti minus f xi minus 1 ti minus 1 all over h. So this allows us to write the series expansion as shown here. So xi plus 1 is equal to xi plus 3h over 2 f of xi ti minus h over 2 f xi minus 1 ti minus 1 plus order h cubed. So we have this order h cubed here. So the Adams-Bashforth method is second order accurate globally, as we the local time step is one order higher than the global accuracy. So let's apply this method to the model problem. And this leads us to the following, the linear difference equation shown here. So now we can assume solutions of the form sigma n equals, or xn equals sigma to the power n x0, which results in a quadratic equation for sigma with roots as shown here. So now let's use the power series expansion for the square root portion, and we see that we can expand it with this series here. So this means that we can write our roots sigma 1 and sigma 2 as shown here. So sigma 1 is equal to 1 plus lambda h plus 1 over 2 lambda squared h squared plus order h cubed, and sigma 2 is equal to 1/2 lambda h minus 1/2 lambda squared h squared plus order h cubed. So here from this root, we can see again that it's second order accurate, and that here we can see that, and this is the spurious root. And the spurious root for the Adams-Bashforth appears to be less dangerous than for the leapfrog method. You can see that as h goes to 0, the spurious root will also approach 0. And this is the stability diagram for the Adams-Bashforth method. You can see that the stability region crosses the real axis at -1. So this is more limiting than the explicit Euler and the second order Runge-Kutta methods. We can also see that it's only tangent to the imaginary axis, so it doesn't actually include the imaginary axis. So strictly speaking, it is unstable for purely imaginary lambda, but it turns out that the instability is very mild. And this is just a comparison of the stability diagrams for some of the methods that we've looked at recently. So this shows the second order Runge-Kutta method here, the fourth order Runge-Kutta method here, the leapfrog method just along the imaginary axis, and the Adams-Bashforth method. So let's look at an example, the same example that we've considered previously. So we have the second order ODE, y double prime plus omega squared y is equal to 0, with initial conditions 1, 0 is equal to y naught, and y prime of 0 is equal to 0. And we want to solve this using the leapfrog and Adams-Bashforth methods. So as usual, we need to write this as this second order ODE as a system of two first order ODEs. So we set y1 is equal to, y1 prime is equal to y2, y2 prime is equal to minus omega squared y1. And our initial conditions become y1 of 0 is equal to y0, and y1 of 0 is equal to y naught, and y2 of 0 is equal to 0. So using the leapfrog method, we can write our equations here, and using the Adams-Bashforth method, our equations become those shown here. So multi-step methods are not self-starting, so we must use a single step method to calculate the first time step. So let's use explicit Euler. So for our initial conditions, y1 of 0 is equal to y naught, and y2 of 0 is equal to 0. Let's use explicit Euler to find out what y1 at 1 and y2 at 1 are, as shown here. And now we can use these in both the leapfrog and the Adams-Bashforth methods and proceed from time step 2 and on. So this shows the result for y naught equals 1, omega equals 4, and h is equal to 0.1. You can see the black line is the exact solution, the blue line is the blue dashed line is the leapfrog, and the orange dashed line is Adams-Bashforth. So the leapfrog is stable, and has very little amplitude error. The phase error is significant and increases with time, as you can see. The Adams-Bashforth method, shown in orange, is mildly unstable. And so the amplitude and the phase error both increase with time.